All right, my good friends, it is 1:30 in the morning. I made the mistake of having a Starbucks tonight at 10 o'clock, and so it's 1:30 now. I can't sleep, so I decided to get up and make a video. So here we go. Unit 16, Reaction Kinetics, 12.5, Reaction Mechanisms, if you're following me in the Zoom doll book. Here we go. What do we mean by a reaction mechanism? Well, a mechanism is simply a set of steps that represents a chemical reaction. In other words, most chemical reactions don't occur in one fell swoop. In other words, they happen over a period of time, over a period of steps, right? So let's take this reaction right here. Let's take a look at nitrogen dioxide gas plus CO gas yielding NO gas plus CO2 gas. So that is a chemical reaction, and that reaction tells us a lot about what the reactants are and what the products are, and even tells us the stoichiometry. It's a 1-to-1 to 1-to-1 mole to mole to mole to mole relationship. But what it doesn't tell us is the series of steps, and it certainly doesn't tell us in and of itself the rate law for that reaction. It doesn't tell us the rate law for that reaction. But let's just say that we do some studies, some analytical experiments, and we determine that the rate law for this experiment is this. Its rate is equal to K times the concentration of NO2 squared. So that is the rate law. Maybe we've used the initial rate method, for example, to determine that rate law. So what does that tell us? What does that tell us about the mechanism, right? What does that tell us about the way that this reaction happens? And by the way, one of the big reasons that we discuss reaction kinetics is because scientists are very interested in these reaction mechanisms. They want to know precisely how these reactions occur. And rate laws tell us a lot about how they happen. So let's take a look at the mechanism, or at least a potential mechanism, for this reaction that we're showing up here. One possible candidate for a mechanism is that two molecules of NO2 will collide one another. We'll call this the first step, of course. Two molecules of NO2 will collide against each other with sufficient energy and in the correct orientation and produce NO3 gas and NO gas. In a second step, then, a subsequent step, that NO3 gas will collide with CO, carbon monoxide gas, to produce the products NO2 and CO2 gas. So the question is this a reasonable mechanism, right? Is this a possible scenario, two-step process for how this initial reaction might have happened? Well, in answering that question, what we want to do is we want to start with actually a couple of definitions. The first one we want to talk about is an intermediate. What do we mean by an intermediate? Well, it's a species that is neither a reactant nor a product. You don't see it in the actual reaction, the reactants or the products, but it is produced and consumed during the reaction sequence. Now, I want you to take a look at this mechanism, this two-step mechanism, and see if you can find anything that is produced and then consumed without showing up as either a reactant or a product. Give you a second. All right, NO3, that's it. NO3 is produced and then consumed, and you never see it as a reactant or as a product. We call that an intermediate. Now, let's not confuse that with catalyst, right? Catalyst. Now, we've all learned that catalysts speed up the rate of the reaction, and we've talked about how that happens by lowering of activation energy. If you're going to have a catalyst in a chemical reaction, you're going to see that catalyst showing up because you put it there. I'll just call it X in this case, at the beginning and then again at the end, right? You're going to see it at the very front and the very back, right? It's not going to be consumed by the reaction mechanism or in the series of reaction steps. It's there at the beginning and at the end. So that is what we call a catalyst. So let's not confuse those two. Now, the next step, by the way, that I need to talk about is the next thing I need to talk about is the fact that, generally speaking, one of the steps in the reaction mechanism is a slow step. Let's say this one right here is the slow step, right? And the other one is quite fast in comparison, right? So the first one is slow, the second one's fast. Let me make that W a little bit better there. There we go. So Why is that important? Well, as it turns out, it is the slow step that determines the reaction rate for the overall reaction. Now let's think about this. Let's just say we're running a relay, right? We're running a relay and you have 3 really fast people on the relay team, and then you have 1 really slow guy or girl on the team. All right? Who's going to be the one that's going to determine the time? It's going to be that slow one, right? In other words, you're only as good as your weakest link, right? And the same thing is true about the reaction mechanism. The reaction cannot proceed faster than the slow step can proceed. All right? So we call that the rate limiting step, the slow step. All right? Now, I want to talk a little bit about unimolecularity. What do we mean by, or excuse me, molecularity? What do we mean by molecularity? Well, molecularity means the number of molecules that are present in a particular step, right? So if you have one step or one molecule involved, say you have a molecule that simply disintegrates, falls apart, we're going to call that unimolecular. So one molecule, unimolecular. Let's just say that you have 2 molecules, right? That's going to be called bimolecular. So if you have 2 molecules, that's bimolecular. Termolecular is 3, but it's rare, right? So it's going to be a rare situation where 3 different molecules are going to collide in exactly the correct orientation with sufficient kinetic energy to make a reaction go. So termolecular reactions are very rare. But we certainly do see unimolecular and bimolecular reactions. So what does that tell us about the reaction? Well, as it turns out, it tells us a lot. It tells us the rate law for that particular step, right? So, for example, if we have a unimolecular reaction, right, then we know the rate law for that step is going to be rate is equal to K times A to the first power. We can just say A, right? But if you have a bimolecular situation, that was for unimolecular situations. If you have a bimolecular situation where you have 2 particles that are involved in that rate determining step, we would call that bimolecular. Now, the rate law could be one of 2 things depending upon whether you have 2 of the same molecule banging into each other or 2 different molecules banging into each other to give the collision necessary for the reaction to go. So if it's the same molecule, if it's the same type of molecule banging into each other, the rate law would be rate is equal to K times A squared. 2 molecules involved, but they're the same. If it's 2 different molecules, rate is equal to K times the concentration of each of those 2 different molecules, okay? Each of those 2 different molecules. All right. One other thing, and I'm going to pull up here just to show you this, that's very important about the rate law for a reaction and also for individual steps, because this is important, okay? All right. So what we did was we looked at a general reaction. This is the reaction up here. NO2 plus CO gas yields NO gas plus CO2 gas, right? Now, remember that when we wrote the rate law, for this particular reaction, that initially we did not know what the rate, in other words, we didn't know what the rate law was going to be until we did empirical data. Now, I'm telling you now that it has been discovered that the rate law is equal to K times the concentration of NO2 squared, all right? So in other words, CO was 0 order because it's not showing up in the rate law, and NO2 is 2nd order, right? But you must do that kind of experiment or the multiple trials and then do a experimental data analysis to determine what the rate law is. But that's not true for the individual step. So each individual step also has its own K. We'll call this one K sub 1 and this one K sub 2, just like that, right? So if you want to determine the rate law for a particular step in the reaction mechanism, it is just fine to be able to determine the the rate from the coefficients in front of each of the reactants. So for example, I could write for this one, the rate is equal to K sub 1 times the concentration of NO2 squared. All right? So that is the rate law for this first step, the slow step. What about the second step? What's the rate law for that one? Well, as it turns out, we've got two different reactants, NO3 and CO. So we would say rate is equal to K2, K sub 2, times NO3, concentration of NO3, times the concentration. I'm going to move this over just a bit. You'll remember, I'll put slow on the other side, but you'll remember, it's this one right here. This is the slow step, the first one. All right? So it's concentration of NO3 to the first power times the concentration of CO also to the first power. So let me just review. For the overall reaction, the one we started with up here, you cannot tell what the rate law is until you've done experimental analysis. All right? Now, we did that experimental analysis. As it turns out, we got K is equal to, a rate is equal to K times the concentration of NO2 squared. So we did it and got that rate law, right? But for the individual steps of the mechanism, you can use the coefficients. So there's a 1 here, a 1 here, and a 1 here, and a 1 here. So you can use those coefficients in the rate law for the individual steps. Why is that important? Well, in looking at a mechanism and trying to determine whether that mechanism is a feasible one or not, two things must happen. You must satisfy two requirements. The first is that the sum of the elementary steps must give the overall balanced equation for the reaction. So let's see if that's happened. So let's go back to our mechanism, and I'll put the mechanism and the reaction itself on the same screen so you can see this, okay? If you look at the NO3, remember that was an intermediate and canceled out. So what's left? We've got NO2 on the left. We've got another NO2 on the left, but one of those NO2 is going to cancel with this NO2, right? And so we've got one NO2 net on the left plus A on the left. We've got a CO right here, just like we've got in the overall reaction. On the right-hand side, we've got an NO gas, just like that. And we've got CO2 gas. Well, it looks like it passes muster on that first requirement. In other words, the sum of the the sum of the reactions in the individual steps of the mechanism equal to the overall balanced equation for the reaction. Now, here's the second kind of criteria that must be overcome. Number 2 says the mechanism must agree with the experimentally determined rate law. And that's for the slow step, okay? The mechanism must agree with the experimentally determined rate law. So when we say the mechanism, we mean the slow step of the mechanism. So let's go back up to the mechanism once again and look to see what the rate law was. The rate law was this right here. Let me change color so we can see this a little bit more clearly. The rate law for the slow step, remember the first one was rate is equal to K times the concentration of NO2 squared. Well, that's exactly the rate law that we determined by using empirical data for the overall reaction, isn't it? So that means that the second criterion is held. In other words, the rate law for the slow step of the mechanism is equal to the rate law overall. Now, that doesn't absolutely guarantee that this is the correct mechanism, all right? It doesn't guarantee it, but it's at least a candidate. I'll see you in the next one. Bye-bye.